Here's another line integral we're going to calculate. So we have a vector field, f of xy is y squared x, and my parameterized curve is a counterclockwise path around the perimeter of the rectangle, where x goes from 0 to 2 and y goes from 0 to 3. So, like the other line integrals we've done, we need to determine which method to use. So the method where you integrate from a to b with a function of t dt, that can be used, by the way, on anything, on any line integral. Sometimes it's harder, sometimes it's easier, depends on what the vector field and the parameterization is. However, we have other methods. We have the fundamental theorem of line integral, and we have Green's theorem that can make things a lot easier for us. So you want to check to see if you can use one of those theorems. So one of the first things that you want to do is check to see if your f is path independent. So that means I'm going to take the partial of f2 with respect to y. Nope. Partial of f2 with respect to x. Sorry about that. And I want to compare it to the partial of f1 with respect to y. Partial of f2 with respect to x is 1. Partial of f1 with respect to y is 2y. They are not equal, so they are not path independent. Now, let's check to see if we can use Green's theorem. Now, in order to use Green's theorem, we have to check what C looks like. Now, it says a counterclockwise path around the perimeter of a rectangle. So x goes from 0 to 2, y goes from 0 to 3, and I move in a counterclockwise movement. So I move in this direction, then I move in this direction, then this direction, then this direction, and I keep moving around like that. So according to Green's theorem, in order for me to be able to use it, my parameterized curve has to be simple, piecewise smooth, closed curve, upon which when I walk around in the direction, my interior is on the left. So imagine yourself following this line, walking along the line. Your left arm is going to be on the inside, so that means that Green's theorem can be used here. Okay? That's an exclamation point if you don't know. Haha. So what does Green's theorem say? How do we calculate a line integral with Green's theorem? So if I want to calculate the line integral over C of f dot dr, that's equal to the double integral over the region R of the curl of f dA. Now dA and R, this is a region in a two-dimensional space xy. dA is the change in x with respect to change in x and the change in y. So this is a double integral or iterated integral depending on your teacher. And the way you determine that is that's area, that's a region, that's this space, the region that around which the curve falls. Now, we also would be nice to define what the curl is. Well, you actually utilize these two things to do the curl. The curl of any function or any vector field f is equal to the partial of f2 with respect to x minus the partial of f1 with respect to y. Now, if you do all this work ahead of time, that's easy to calculate. So if I calculate the curl of my particular vector field, that's going to be 1 minus 2y. So this guy gets inputted into my integral in order to solve the line integral. So let me scroll up a little bit so we have more room. So this is going to be a double integral. My function is going to be 1 minus 2y because that's the curl. And then because this is rectangular, this makes it extremely easy to find the bounds using rectangular coordinates, namely dx, dy. So, and you can do dy dx, it doesn't matter, just make sure your limits are right. So if I do my change in x, that means that as I move in this direction, I hit x equals 0 and x equal 2 first, the functions. And then I restrict them with y going from 0 to 3 in order to create my region R in the plane. Notice C bounds R to make my double integral. And then I just have to use double integral methods to calculate this double integral. And let's see what it turns out to be. So this is equal to the integral from 0 to 3. And I'm going to take the integral of this with respect to x. So since there's no x's in here, I can just treat that like a constant. So it's going to be 1 minus 2y x from 0 to 2 dy. That's going to equal 0 to 3, 1 minus 2y times 2. Well, remember I have to plug in 2 for x and then subtract plugging in 0 for x, but 2 minus 0 is 2, so I am good to go with that. Then I'm going to take the integral with respect to y. Sorry, I had to think about something there really quick. All right, if I take the integral with respect to y, I get y minus 2y squared over 2 from 0 to 3. Then that gives me 2 times 3 minus 2y squared, or 3 squared over 2 minus 2 times 0. It's not very neat. The 2's can cancel. So what I'm left with is 2 times 3 minus 9, which is going to be 2 times negative 6, which is negative 12. So again, interpreting that this negative sign means that my parameterization is going mostly against the flow of the vector field, and the number itself is a value of work for how much work either the vector field does trying to push it into the flow, or the parameterization trying to get through the movement of the vector field.